today. And I also like to thank a number of colleagues with whom I consulted for this talk. As you will see very quickly, that I'm clearly not going to be an expert in everything that I'm going to talk about. So I'd like to thank the colleagues who had helped me, given me their views, opinions, information, and so on. And also like to thank a student of mine. All my colleagues are Louis Chen, Chin Chi Wai, and Shen Zuowei in the mathematics department. And then a student of mine, Yang Yi, who prepared the first draft of the PowerPoint slides. Okay, now I'm going to start with an example that everybody probably knows too well. And that is what's called prime numbers. And prime numbers, as we know, are numbers which are divisible by 1 and by themselves, but of course we exclude 1 as we consider the number 1 to be, well, maybe just a bit too trivial to even mention. So numbers like 2, 3, 5, 7, 11, 13, and so on are prime numbers. Now, prime numbers are what we call the basic building blocks of numbers. Going back to the time of Euclid, it was already known that every natural number could be factorized into the product of powers of primes. So in that sense, every number comes from prime number. And of course, if you know what's called rational numbers and real numbers, and then you see that the rational numbers come from dividing two natural numbers, and therefore, in a sense, they also come from prime numbers. And real numbers are nothing but what we call, in mathematical terms, the completion of rational numbers, and therefore the source also goes back to prime numbers. And then if you go to complex numbers, which are just complex numbers with what we call the real part and imaginary part, then of course the origin can be traced back to the prime numbers. Now, it was Euclid. Where am I supposed to stand? My mobile. Euclid had proof. He gave the first proof of the infinitude of prime numbers. He showed that one cannot finish counting the primes. It goes on forever and ever, so to speak. And the proof that Euclid gave was really ingenious, and it's short, simple, but really elegant. But I will not talk about that. The question really is, all right, we know that there are infinitely many prime numbers. There are the prime numbers form the building blocks for all numbers, but really, what do we know? What else do we know about the prime numbers? Well, here is a very short table of the distribution, what we call the distribution of prime numbers. On the right-hand side, well, x is just any number, any number, 3.14156, for example, if you want. And then pi of x is just the number of primes that are less than or equal to x. So, for example, if x is equal to 10, you would have 4 prime numbers. That would be 2, 3, 5, 7. And then if x is 100, there will be 25 prime numbers. If you do counting, you see that that's indeed the case. But going down to the very last row, if x is 10 to the power 23, that's a huge, huge thing. We know today that there are 1.9 times 10 to the 21 many prime numbers. Obviously, this kind of computation cannot be done by hand, and we need the help of powerful computers. And as computers become more and more powerful, well, we get more and more information. But what we know is really that there does not seem to be any pattern in the distribution of numbers, right? There's no nice formula that can give us what pi of x is given x. It's not something like x squared plus 3 or something like that. They seem to be all over the place. Or maybe they are not, because they are not that random in the sense that you don't know where they are. You can actually compute. Given a number x, you can actually find pi of x with enough time and resource and all that. In theory, anyway, you can actually do it. So in that sense, they are not random. On the other hand, there seems to be no way of really predicting exactly, short of going to that point and do the calculation, to really arrive at the number of primes less than a given number like x. So in that sense, we can call the prime numbers to be pseudo-prime. This is not a technical definition. It's just a convenient way of saying that. So because of that, the urge to understand the distribution of prime numbers has become stronger and stronger. In fact, I would say perhaps since Euclid's time, people try all sorts of ways to try to come up with something that could describe the distribution of prime numbers. And of course, this is just a digression. If you are familiar with some of the major topics in major computer science, in modern computer science, you know that prime numbers, the study of prime numbers is actually a very important subject in cryptography. In fact, a lot of, current technology in electronic commerce for computer security uses different types of coding techniques, keys that will encode some large prime numbers in the information so that information transmission over public sources will remain secret and confidential. So, well, that's an application of prime numbers which I will not dwell upon. Now, so because prime numbers are so hard to predict in terms of computing where they are and so on, I would say since maybe the 1600s or 1500s to the 1600s, mathematicians spent a lot of time trying to come up with ways of predicting the distribution of prime numbers. And the ways got better and better. Here's a picture of, it's a very simple picture of how primes look. I mean, it's a translation of what we saw in the previous slide to a picture. Here you see a triangle. In simple terms, it means that as x gets bigger and bigger, the number of primes go up. And here, of course, we just go to a small number. We don't go to 10 to the 23. But because of Euclid's result that there are infinitely many primes, we know that the curve will have to go up, right? But in what fashion, that is not clear. Now, this was a formula that was conjectured by Gauss. And the twiddle in between means something like more or less equal to, meaning that if you want to count the number of primes not exceeding x, the number of primes less than or equal to x, call it pi x, then asymptotically, as x goes to infinity, it should approach the value on the right, which is the integral from 2 to infinity of 1 over log x dx. Now, there are different types of different formulas that mathematicians came up with to try to describe the distribution of prime numbers. There's one other formula that I think came from, was it Euler? That says that pi of x is approximately equal to x over log x. But Gauss had a different formula, which is this one, that says that pi x is approximately equal to this. Well, of course, in the end, both formulas are correct in the sense that as x goes to infinity, the error, the difference between pi x and the proposed formula should go to 0. The question, I guess, is really in the speed with which this convergence goes. Now, this was called the prime number theorem. Well, at the time it was proposed, it was just a prime number conjecture. In other words, here's a conjecture saying that to calculate the number of primes less than or equal to x, integrate from x from 2 to infinity of 1 over log x, right? And around 1890 or so, or 1892, the French Academy in Paris set this as a prize problem for mathematicians of the day to establish the prime number theorem. Of course, people believe that this ought to be correct because using the powers of the computation available in those days, I don't know what they had in those days, but at least they could use their hands. And Gauss himself did compute quite a number of cases and conjecture that this was the formula. And no one would actually doubt Gauss. If Gauss said so, it had to be so, that sort of thing. And so this was posed as a problem for a major mathematical prize by the French Academy in the 1890s. Now, however, that conjecture that pi x is approximately equal to the integral of 2 to the infinity of 1 over log x was, as I said, proposed by Gauss, and that was well before that. It was around 1820 or 1825, so there was many years before it became a prize problem. And in 1859, by the way, in 1859, Bernhard Riemann, some of you may have heard his name if you have studied calculus. Riemann integral is a basic subject in calculus. And of course, Riemann was one of the, I would say, greatest mathematicians in the history of mathematics. In the year 1859, Riemann was, at the age of 31, he was elected to the German Academy, where he delivered a paper on the occasion of that election. And the title of that paper was called On the Number of Primes Less Than a Given Number. Of course, it was in German. And in there, he introduced the following formula, what we call the zeta function. Zeta of s is equal to the summation from 1 to infinity of 1 over ns. And if you write it out, it's just 1 plus 1 over 2s to the power s plus 1 over 3 to the power s, and so on and so forth, where s is a complex number, x plus iy. X is what we call real part, y is called the imaginary part of a complex number. If you remember your calculus, you actually have seen something like this, but not in this form. Namely, you would have seen the so-called harmonic series, summation of 1 over n, for n from 1 to infinity. And then you would remember that that is a good example of a divergent infinite series. So that series, 1 over summation 1 over n, was known long time ago, well before Riemann. And it was Euler who looked at that function and considered the powers of 1 over n. So he considered 1 over n to the power s. In that case, he was looking at S as a real number, maybe summation 1 over n squared or 1 over n cubed. S could be 2 or 3 and so on and so forth. But actually Euler considered all possible real numbers. And Euler was the first person, I believe, who showed that summation 1 over n squared is equal to pi squared over 6. Somehow, I don't know, when I was teaching engineering mathematics, I was required to prove this. I don't know what relevance it has to engineering, but it was one of the things that was done for engineering students. Now, the year 1859, when Riemann gave his paper and came up with this function, and we will soon know why he came up with this function, introduced this function, that's a generalization of what Euler did. So Riemann extended this function from real numbers S to complex numbers. And then he showed in modern terms that this function has a meromorphic extension to the entire complex plane, except that at the point S equal to 1, where it has a simple pole. So that means that this function, if you look at it as a complex number function, is defined everywhere in the complex plane, except at the place where S is equal to 1. And we know, as I said earlier, when S is equal to 1, it gives you the harmonic series, which is divergent. The year 1859, as I was saying, was a very important year. That was the year also when Darwin published his Origin of Species. As you know, that this is the 150th anniversary of the publication of Darwin's book. And that was also the year that Riemann introduced the Riemann zeta function. As it turned out, it was also a significant event, perhaps the most significant. Well, this could be subjective to the mathematicians. Riemann, as you can see, did not live long. Born 1826, died 1866, just about 40 years. So this was 8 or 9 years before his death that he presented this talk. The question really is the way Riemann put it. What are the zeros of zeta S? In other words, which complex numbers S will let you have zeta of S equal to 0? So we have an infinite series like this. S is a complex number, sum it up, and so on. And which S will give you zeta S equal to 0? Now, what does this have to do with prime numbers? That's the first question, I guess, you might ask, since I started with prime numbers. And secondly, why would one look at the zeros of zeta function? Why not zeta S equal to 1 or 2 and so on and so forth? Now, if we look at the zeta function, today we know quite a bit about the zeta function. And here's something that I can talk about. First of all, for all even negative numbers, S, if S is equal to minus 2, minus 4, minus 6, minus 10, minus 20, and so on and so forth, zeta of S is equal to 0. These are the so-called trivial zeros. Trivial in the sense that they're easy to compute, right? Easy to verify, and one can tell with some elementary knowledge of complex analysis, you can get that. So trivial zeros are in general not interesting, and so we put them aside. Then there are so-called non-trivial zeros of the zeta function. In other words, there are complex numbers S where zeta S is equal to 0, and they are not equal to minus 2, minus 4, and so on and so forth. But where are they? In fact, what we know is that all the so-called non-trivial zeros, where zeta S is equal to 0, will have the form where the real part x lies always between 0 and 1. This is what is called the critical strip. Yes. Here's a picture. The big column that you see represents the critical strip. So this is 0, the real part, that one is 1. And it goes from minus infinity, the imaginary part, all the way to positive infinity. The solid red line you see divides this strip into 2 equal halves. And that's at a place where the real part is equal to half. X is equal to half. And it is known that all the zeros of this zeta function will lie on the critical strip. Right? Now, this critical line, the red line, is of particular interest. Let us see why. Here's a picture of what happens. Originally, I wanted to have computer animation of this thing, but when I tried out on my computer, sometimes it hangs, sometimes it didn't. I decided not to embarrass myself. So what you see there is the result of computing zeta of S as you travel along the red line. Right? So imagine that you have two complex planes, one on the left, one on the right. The left-hand side is the input. The one on the right-hand side is the output. So the input here, you just input the points along the red line. And what you get is the one on the right-hand side. So what happens is that when you are at the real axis, right? That means that when you are at a point where S is equal to 1/2 plus 0, the imaginary part is 0, you are actually here on the right, that point, on the tip on left-hand side. Then as you travel up, it actually goes down and then goes up in a clockwise direction, moves one lap, touches 0, and another lap touches 0, another lap touches 0. In other words, it goes in sort of almost like concentric circles kind of thing, but it always comes back to 0. Right? And when it comes back to 0, this is where zeta of S is equal to 0. So when zeta S is equal to 0, the image is actually down there. So as you move up, the critical line, or move down, in fact, it's known that if zeta S is equal to 0, then its complex conjugate, that means the mirror image down below, is also a 0 of the zeta function. So as you move up the critical line, which is the same as you move down, you actually, on the right-hand side, you'll be circling around and then you come back to 0 from time to time. That means that not everything on the red line is a 0, but there are many points on the red line which are 0. Okay. Now, what do we know about this? Riemann himself computed, I think, at least 3 zeros, non-trivial zeros for the zeta function. I guess in those days, maybe because of his intuition and his belief, he came up with something. He said, well, if the first 3 zeros are 0, maybe everything else is 0. I mean, it must be. So he computed the first 3 zeros, and they all lie on the critical line, meaning the real part is equal to half. Right? But we know a lot more than that these days. It is known that at least 2/5 of the zeros, we know they have to be on the critical strip, but where on the critical strip? It's known at least 2/5 of the zeros lie on the critical line. In fact, we know more than that, that there are at least, the first 10 to the power 23 non-trivial zeros of the zeta function all lie on the red line, on the critical line. The Riemann hypothesis, as Riemann formulated it, says that, in fact, you can only find solutions on the red line. In other words, although you have a critical strip, mathematically it's proved that all the zeros will lie between on the critical strip. The hypothesis that the Riemann made was that, in fact, all the zeros must lie on the red line and nowhere else. Right? This is called the Riemann hypothesis, and it has become, well, many mathematicians believe that this is the problem in mathematics to solve today. Right? It remains open, of course, and many attempts. I guess every year there will be some people who claim that they've got it, but not quite. There's also $1 million prize attached to this one by the Clay Institute in the US. And David Hilbert, in the year 1900, when he presented the talk called The Future of Mathematics, or called Mathematical Problems, I guess, in Paris, 1900, International Congress of Mathematicians, listed Riemann hypothesis as number 8 among his 23 problems that he believed, whose solutions he believed would change mathematics. And many of the 23 problems have been solved, but this one remains untouched at this point. That question really, so why was Riemann interested in the zeros of the zeta function? As it turned out, it has deep connection with number theory, with the distribution of prime numbers. In particular, if Riemann hypothesis were true, then prime number theorem would follow. Of course, when Riemann proposed this thing, the prime number theorem was still an open problem. It had not been solved. It was only solved maybe 30 or 30-some years later. So here is an indication, or at least certainly some evidence to support the truth of the Riemann hypothesis, that if you assume the Riemann hypothesis, then the actual count, given x is on the left-hand side, pi x is the number of primes, and then if you assume the Riemann hypothesis and use the formula that was given, the prime number theorem formula, then you see that they're really very close, especially when it goes to infinity, right? At a place where you have got x equal to 10 to the 12, the error is actually just around 2 times 10 to the minus 5, right? So why is it that the hypothesis itself would have a bearing, in fact a significant bearing on the distribution of prime numbers? It's a mystery. But Jacques Hadamard, along with another mathematician, de la Vaupoisson, independently proved the prime number theorem. This was in the year 1896, just 4 years before the turn of the century, around the same time, right? And actually, Hadamard was writing his PhD thesis, and then I think after completing the thesis, somebody looked at it and suggested maybe this could be modified and actually would lead to the solution of the prime number theorem. And this was indeed the case. Of course, he did it without the use of Riemann hypothesis. Otherwise, that would be a problem since the Riemann hypothesis is still open. Hadamard, as you can see, lived a long time, 98 years old. And many French mathematicians live a long time. I think it has to do with wines, obviously, right? But he himself, his life he was rather tragic. He had 3 children and all died before him. One died in the First World War, one died in the Second World War, and then the third one also died young. I will come back to him later on. But now I'd like to move very quickly to the year 1972. Now it's fast forward. The year 1972, something rather surprising happened. Hugh Montgomery